Swayam Prabha. Digital India. Educated India.
Welcome back. We just tried to read one preposition written in the language of L-type before, and here is the second one. We can read a few more depending on the time and everything. Now, this one is a little more abstract than the previous one. So, what is it we are supposed to read this one? What is it this is claiming? Now, we can see that we are very we are making comments on any one plus predicates. In fact, we are making comments on all one plus predicates. This is one thing we couldn't do in the previous languages. In this language, so this language helps us do this. Now, this is a direct, this is a explicit example of commenting about predicates. Now, this is saying that there must be at least one entity, because it belongs to V0E, at least one entity such that for all one plus predicates, if a specific property, this is a constant, this is not a variable, if a specific property applies to that one plus predicate, then that one plus predicate will be applied to that entity. Now, it is something like saying that there is some entity there must be at least one entity V0E, one entity such that if a specific, if such that if like the language always become complicated here, we don't know, like we find it difficult to express this in English, but I'll try my best. As I said that this is it presents a specific property. What is that property? It is a property such that if it belongs to a one plus predicate, practically any one plus predicate, then that one plus predicate will apply to that entity. So, it is basically about some property, it is basically about the existence of some entity. Now, once again I find it difficult to express it, I try my best. It is about one entity or about some entities such that all one plus predicates are such that if they have a certain property, then they will be applied to that entity. So, there must be one such entity in our whole system. This is what this is trying to say, and we are trying to read it. We are not trying to see this, verify this, the truth of it against the model we have got, but the point here is not whether this is true or not. The point is whether we can read this thing. That we can do. Yes, I could not translate it into normal English very successfully. It is not really possible, but we can roughly understand what it is trying to say. And now, because in our ordinary language, very rarely we actually talk about predicates. So, we find it very difficult to talk about predicates and stuff. That is also another reason we find this difficult to translate. Anyways, we wanted to read this and we are reading. So, we have seen so far that we can now define. So, the achievements I am going to calculate, we can now define something like non, which we could not do in L1. We can define something like R0, the object deletion function, or RS, the subject deletion function. We can now define all these things by using our framework of L type, and this effect was not achieved before. And then also we have created a higher order language for talking about predicates of predicates at any level. So, after having seen this, we now go to another version, another updated version of a higher order predicate semantics. So, and this is based on lambda calculus. We started with L type, and then now we switch to L lambda. We need to learn the lambda operation for doing this. Now, lambda operators are simplifiers. We will talk a lot about lambda expressions. We will have at least 2 sessions or nearly 2 sessions on this, because it is so very important. Now, what is lambda operation? By the way, lambda operation or this lambda calculus was invented by a brilliant mathematician, logician called Alonzo Church in 1930s, and after it was invented, it was hugely used, and in almost every logical mathematical system, in almost every computational system, you now people have to use this lambda calculus. What does it do? A lambda operator is a function splitter. What I mean by that? Anything we had before now can be used as a lambda expression, and we can do a lot more as we are updating. One thing we must have noticed, we have been updating our understanding of the natural language, and what was the original agenda? It was to show that there is no fundamental difference, no significant difference between an artificial language and a natural language. So, and we have been seeing that Montague has kept his promise so far. He has covered so many things by using different tools. So, here is another tool, this lambda calculus. It can do things which were not possible previously in the semantic system. So, what are those? I will talk about those after we just see this operation. So, it is something like this. We have lambda x and something x, whatever, and then we give alpha to it. So, this is a function and we give alpha to it as an argument. How does it simplify it? It seems very, very easy and very, very handy. What happens is alpha goes in and replaces x and sits here. This is what lambda functions do. For example, you can all the time say that lambda x mx, and then you give, say, a name J, which stands for John. Actually, this lambda shouldn't be there at all, because the whole point is we have converted. So this is one of my typing errors. So, now this looks fine. So, when I give this j to this lambda operator, what it does is lambda goes along with x and j comes in, and we are just left with mj. That is it. So, this is what the lambda operator does. Now, what is the point? We will talk about that. What, like, such an easy, such a handy thing. yes, fine, we accept, we understand that it's a very easy operation, but the point is, what is it doing? We shall see what it is doing. What it is doing is something unprecedented in the history of logic and mathematics. We go to the next slide to understand the lambda operators. We have just two examples to see what is happening. Now, what will be the simplification here? Lambda x 2x plus 3 equals 13. What will happen is lambda will go and 5 is the argument given to it. 5 comes in after replacing x. So, we have 2 times 5 plus 3, that makes it 13, which means that the sentence inside, it can be true, it can be false, it can be anything, but in this case it is true. So, it defines practically it defines this function 2x plus 3 equals 13. It just this lambda expression defines this function. How we shall see that? And another one, slightly more abstract, slightly more complex, but we can see this. Now, this says that this has a quantified structure. This says that lambda x all y less than 7, if y is less than 7, then x is greater than 2 y minus x, and that takes 11 as an argument. And then what happens, we will see. Now, so this will, now you see what goes out, the lambda concerns x, not y. Y is quantified, and lambda just works on the unquantified thing, because lambda itself is a binder like this quantifier. Now, when 11 comes in, we can check what is it the statement is trying to say. It is saying that for all y, if y is less than 7, then now x has 11 is greater than 2 y minus 11. Is it a true sentence or not? It is true, because y less than 7, which is, then there are 6 cases. So, the value of y would be from 0 to 6. Now, yes, if y is 0, then y is less than 7, and in this case 11 is greater than 2 y, which is 2 multiplied by 0, y 0 minus 11, which makes it 0 minus 11, that is minus 11, and it is true that 11 is greater than minus 11. So, true. Then we consider the next value, that is y is 1. So, if y is 1, then let us see whether this holds. 2 multiplied by 1, that is 2 minus 11, which is once again true, because this will be minus 9. So, this way we just go up, and finally y is 6 still. So, when y is 6, then also 11 is greater than 2 multiplied by 6, which is 12 minus 11, which is 1, and 11 is greater than 1. So, yes, so in a very complex manner, although it is a very simple function, what it can do can be very complicated. In a very complex manner, this is actually defining this whole function, that is, for all y, if y is less than 7, then x is greater than 2 y minus x. So, lambda is a definition maker. That is not the only feature of the lambda operator. There are many other features. We will try to discover all those features. We start here. So, then we go to the general rules and stuff, but before going there, we can see how the lambda operator works. I said it does two things: one, defining, and two, splitting. So, lambda operators are function splitters. You can have a complex function, a combined function, and then a function which is a combination of several functions. So, the lambda operator can split that complex function into simpler functions. We will see how it can do that, and that is the best achievement. Yes, also the ease of defining something, we will see how it makes defining, the very act of defining, easy. But more than that, also that splitting and defining, the split definition is something lambda calculus can do. So, we see the rules and then we get back to it. So, precisely there are two rules, and first the syntactic rule and then its semantic counterpart, and as I said 2. So, syntactic rule 1, which says that if phi belongs to MET, that means phi is like a sentence. It can be a formula, it can be, I don't know, anything mx or all x mx or anything, and u is a variable of type E, then phi u lambda u phi would belong to E to t. So, it sets the type for this operation. It does not talk about the semantics of it, which it will, the second rule will do, but this will take care of the operation itself. So, once again we see the type. For example, let phi be mx as we said. So, let u be x in this case. So, what is the construction? Then it is a variable of type E, right, of course, because m is E to t, x has to be E. So, then lambda x mx, what kind of a thing is it? This has the type E to t. Why is it E to t? Because it will take an E type thing, and what will it yield? It will yield m j, which is T type. So, you can see that it takes an E type and yields a T type, which means the type of the whole thing would be E to T. Otherwise, it could not have taken E and yielded T, right. We can see how it works. And so, a few other types, for example, when we consider that later. So, the semantics of it, if phi belongs to MET, so phi is, remember this thing is phi, if phi belongs to MET and u where E, that is variable of the first type, E type, lowest type, then alpha u phi, the value of alpha u phi is that function h from A into 1 0 1 or 0, that is the truth values, such that for all individuals E in A, h E equals 1 if and only if phi m g E u is 1 and h E is 0 otherwise. So, what does that mean? We will try to see this. So, for example, we can get back to our model and do this. We can have a practical application of it. This is our old model. We may consider, say, this thing B, we can consider this, that is B can, when B takes, so for example, if we write that B j, what is the value of B j? B j is actually 0. Why is it 0? Because j is actually A and B does not apply to j. Sorry, that is the value of B does not apply to A, and B d is actually 1 and B n is also 1, because d and n are actually B and C, which are included there, which are which fall under the application of B, or rather B is true of d and n In other words, the value of B includes the value of capital B includes B and C. So, this is the case. Now, we remember this, that Bj is 0, Bd is 1 and Bn is 1. Now, we get back to our old format here. This is saying that, so we consider this structure lambda x b x. What will be its value? So, first it defines, so it is the function h from a into 1 to 0 granted, such that for now this is the value part, for all individuals e in a, h e is 1, that is this thing, this takes e and yields 1, if and only if phi, that is just this part, is 1 with respect to all value assignments. So, that is for all e, b x m g e u gives 1. What does that mean? We try to see this case. Now, we know that b j is 0, right. That means at least for one assignment there is at least one e such that b x that is in with respect to that b x m. So, what is that assignment? When a is assigned to x, this assignment gives the value 0, because this one assignment gives this value. So, there is at least one e which happens to be a such that b x with respect to m g a x is 0. That is the reason the value of lambda x b x also will be 0. So, it would be 1. So, in the case of the first predicate, that is m, it would be actually 1, because it applies to all individuals. But so therefore, we could have said that lambda x m x is 1, because with respect to m and g, because all value assignments whichever, so there are 3 assignments, right. So, you take m x with respect to, we check all 3 assignments, I am just omitting the model, that is m. So, a x 1, because a is part of it, and then m x g b x is 1 and m x g c x is also 1. Therefore, these will be 1, but in the case of b it is 0, because at least one assignment, that is this assignment b x with respect to g a x, it is 0. So, this is how the calculation goes. Now, this is the first rule we were trying to understand. The second rule is this. If alpha belongs to m e a. Now, the first rule is a specific rule. It applies only to 1 plus predicates, but it is not our intention. We do not intend to talk about 1 plus predicates only. We want to talk about all predicates, right. So, we need to do something else. We need to have some rule that will take care of all variables. That is why we are giving now this general rule, which says that if alpha belongs to m e a, a is any type, and u belongs to the variable b, then lambda u alpha will belong to the meaningful expression b a. For example, now m x L x y, say for example, this is this thing is actually here alpha is m e a, and this is our alpha, and what is the type of it? It is e to e to t, right. So, and then x is e. Now, so e is our b, and e to t is our a, right. So, then this thing will be of the type b to a, which means e to t. We shall see that. How? For example, suppose you have this L x, and then I just put a constant here. What does it define? Now we will understand how it works as a splitter. Now, for example, look at the difference between lambda x, lambda y, L x y, and lambda x, L x j. This defines all pairs such that the first element loves the second. So, in a sense, this function defines L itself, but the second function, that is this lambda operator, defines those who love j. Who is our j? J is actually a. J is the name for a. A is any individual. So, or let it be John. So, this function defines those who love John, but this function defines love itself. This is how it is a function splitter. This one has split this. So, it has defined just this part, not the entire thing. So, we can see this, we can see the beauty of it when we learn this properly. So, then we go to the semantics part of it. So, because L belongs to e to t and x belongs to e, the type of say L lambda x L x j, and then I give it say I give it Mary M. What will it yield? It will yield M j. And remember, what is it? What is the type of it? E to t. What is the type of it? E. In that case, so when it is B, so this is B, and when this is A, what will be the type of this? Now, this will be the type B A. So, now we are talking, so of course, what it yields is the type T, but we are not talking about this. We are talking about the lambda expression. What does the lambda expression do? The lambda expression takes I'm sorry, once again the type I should the type of L, but I should consider what is alpha here. I just redo it, otherwise it will be slightly confusing. Okay, so alpha is the thing that comes inside. This is alpha. So, for example, we took L x j. This is alpha. So, this is alpha, and what is its type? Its type is actually T, which in our case is A, right. So, this A, and this, then this whole expression, and if the variable belongs to the type B, so what is B here? B is actually E. So, if this is the case, then actually here u is x. So, if that is the case, then this lambda expression will have the type B A, which means it will be E to T. This lambda expression then will belong to M E to T, that is B A. B is E and A is T. Now, we can see that it is true. How? It takes an entity, say M or say J, and it yields a T, that is J likes J, that is John loves himself, or something like that. So, we can see that we can see how it works, and now let us define this one, that is lambda x lambda y L x y. Now, what does this do? This one will take several things. For example, suppose I first give it, it will take things in an order. So, first it takes, say for example, j, then it takes m. So, j goes first. So, x is out. So, the first step will be lambda y L, then j goes in, j m. Sorry, no, m is not there still it is y, and then that takes m, and finally that m goes in, and you are left with L j m, which means that j loves m. Now, this is t, right. So, so now if you want to define this, what is its type, as we have seen that when the variable belongs to the type E, and when the thing that comes out here that belongs to type, what is the type of this? Once again, this is e to t, because it takes an e and yields a t. That is what we can see here. So, what will be the type of this whole lambda expression? The type of this is e to e. So, it takes an e, then it takes another e, and then it yields a t. This will be the type of this expression, and e to t will be the type of this expression. So, this is how lambda expressions are understood, and this has to be interpreted the way we interpreted the specific rule. It is not at all different. I just read it. If alpha belongs to m e a, belongs to var b, then lambda u alpha with respect to m g is that function h from d b into d a, such that for all objects k in d b, h k is equal to the value of alpha, which is this thing. Now, what does that mean? It actually defines whatever is left. We will see that. The model will help us check a few. For example, the first thing is this point, that is, we will establish that this expression lambda x b x defines b itself, and then we will talk about its significance. Now, we will try to demonstrate that this is the case, and here is our demonstration. We know that this b, which is a 1 plus predicate, it belongs to m e e to t, which is a 1 plus predicate. And what is the value of, what does the value of b do? It maps b and c into 1 and a into 0. So, this is there in the model. So, the value of b is actually b and c. So, this is what we just have written. Now, lambda x b x takes something, say alpha, that belongs to m e e, because if this is e to t, it has to take e only, nothing else, and yields b alpha, which is t, which belongs to m e t. Thus, lambda x b x also belongs to m e t. We are trying to, as I said, the demonstration is like this. We are considering the main features of b and lambda x b x, and we try to show that that they are the same thing. So, they are identical, but there are functional differences. We will talk about those. Thus, lambda x b x also belongs to m e e to t. So, we have proven that lambda x b x and b both belong to this type. So, this is one thing we have shown, and the second thing is thus lambda, what is the meaning of this lambda x b x that takes j? The meaning is b j, and you get 0. And so, you see it is exactly what B does. What is the mapping B establishes? It is actually the value of B is actually this mapping, which maps A into 0, B into 1, C into 1. You see this function lambda x b x does the same thing. It takes j, and j, what is the value of j? It is actually A, and it maps that is the meaning of j, the value of j, to 0, and lambda x b x takes d, and which means b, I suppose, and maps that to 1, and lambda x b x takes n, I think, maps that to 1. This is exactly what this mapping is exactly like the mapping of the value of b, that is the denotation of b has the same mapping. So, we have shown two things. One, they must belong, that is lambda x b x and b, they must belong to the same type, which is e to t. We have shown that, and then we have shown that they have the same mapping, which means that these are the two essential features of b or lambda x b x. So, from that we can see that they are the same thing practically, but then what is the point of having any lambda expression? This is a very crucial question. There are many different things that can be achieved by having a lambda expression, which b could not do. For example, lambda x b x is an operation, it is a function. Lambda x b x is a function itself, it can take a value and yield a result. B can't do that, just B is not a function. So, basically lambda x b x is the functional version of B, just B is not a function, but because lambda x b x is a function, we can use it in a dynamic way. We can combine things now by using the lambda expression, the lambda version of B, not just plain and simple B. 1, 2. In the case of this, for example, in the case of 1 plus predicates, there is no splitting because there is just one thing, but when it comes to 2 plus predicates, lambda expressions do something wonderful. What is it? In the case of 2 plus predicates, lambda expressions can split and define something. First of all, what is it? We have seen what exactly it can define. So, we will just make that point clear before we go to the next point. Okay. So, the point is you have this lambda x b x. So, is the same variable. What remains? So, this is the same as b, we have seen that. So, the point is this x goes along with this x, whatever remains is being defined by this. Now, we can consider another 1 plus predicate, which is L j x. Why is it 1 plus predicate? This is a 2 plus predicate, but already it has taken the subject. Remember, when the function takes objects or takes arguments, the order is the object and the subject, but when I represent the function, the order is subject object, right. So, this is the subject and this is the object. So, this is one thing we must remember. There are many reasons for for doing this, but we know that this is there. So, we keep this in mind. Now, this actually what does it define? So, x goes along with this, it defines those who are loved by John, if J stands for John. And on the other hand, if had it been like this, L x j, once again this L x j is the type E to T. Why is it E to T? Because already J is there, one argument it has taken and yielded this, it is a constant. So, it works only in the area of x, that is, it has one unsaturated variable and there it works. So, although L is E to T, L x j is just E to T, because one E has been saturated. So, all I am left with is this much, E to T. Now, this defines, look at the greatness of lambda operators. This defines those who love John, this defines those who John loves, and this defines those who love John. The two different expressions, right? This is one thing you can do. Now, as I said, it defines whatever is left out. So, in this, what is left out is just L j. So, it defines L j. In this case, it defines L something y. So, as I said, so sorry, x is gone. So, I just do this again, because otherwise I will be confused. So, what was it? It was actually lambda x L x j. So, then this x will disappear after I add an argument to it. This x will disappear along with this x. So, now we are left with L and j. Now, it defines the function L j in a sense, that is, it defines whatever is left out, as I said. It defines the lovers of j, and it defines the beloveds of j. So, that is how it splits. Now, I want to define L itself. What do? I use two lambda expressions. After they both are gone, I am left with just L. So, this is equivalent actually to L, whereas this is equivalent to the beloved of John, and this is equivalent to John's lovers. Now, this is equivalent to love itself. This is the beauty of lambda expressions. Without having lambda expressions, we could not differentiate all the levels of this one function L x y. So, we have cooked up three different functions out of this one function L x y or L, then two things, right, two variables or two constants, or there are two spaces, two places after L, that thing. Now, from that we could derive all these three different lambda expressions which stand for three different functions, and they make perfect sense when we put it this way. So, but the point is, yes, this and this go, and whatever is left is the gist of our lambda expression. This is something we have to pick up from this exercise, and then we move on. So, all we can do is we can go to this one. We can now demonstrate that we can demonstrate this thing. Now, we have demonstrated kind of a specific application of lambda expressions. In this, we are showing the general rule of that, right. It is pretty much the same thing. So, let V 0 a be say x, and let v 0 a to b be, for example, m. So, if that is the case, we can rewrite this whole expression as lambda x, then m, or we have a variable here. I am just using a constant, then we will see that through a variable constant, then x, and then we are adding this. So, actually the bracket should be here, the bracket should be here. I just erase this bracket, it is not here. So, yeah, this bracket is wrong. So, in the second expression the bracket is correct. So, now this can be compared, this structure can be compared to this, and then I am giving. So, as I said, v 0 a stands for x. So, wherever you have v 0 here, v 0 a here, you have x here. So, which means it is m. So, a general format of that would be lambda x v, it could be 1 also, anything, v 0 e to t x is v 0 e to t, right. Now, this general format can give you anything. For example, this will cover. So, once again we will see things for once again. So, we can see that this covers things like all x, L x j, which actually, as I said, this defines the lovers of j, and this covers L x. So, we are talking about e to t functions or any a to b functions. It covers L j x. Now, this defines John's beloveds. All these are covered by just one abstract general expression, and also it covers now this is one type and a higher type. So, when v 0 a, let this be once again lambda x, and then this, let this be v 0 a to b, let this be, so for example, L x y. Now, this L is e to t, right, and then when I give x to it, I get I give something else. I give j to it, I get L j y. Now, what is the type of it? Once again, this is it is unsaturated. So, L was e to t and x was e. So, it is now e to t. It is once again unsaturated, right, because L j y wants something. So, basically it says that John loves y, but what is y? Only when y has got a value or some value replaces y, we could have this. So, so it's the same thing. So, then this defines this just the Ly part, right, just the Ly part it defines. So, so whoever loves y is defined by this. So, so this is how it covers this case, and this covers all these cases, and similarly. So, this is actually this, it is a constant, as we said. It could also be a variable in the general rule. This is a variable. So, yeah, so or it could also be, so when you use a variable, you can have a construction like y reaches m y. Even this is okay, right. So, this is one formation, and then the same thing m x with a constant, I just add j, I have m j. So, it is one rule that covers all these things, that much only is said here. And then we have so we understand that when this happens, what remains is the thing that is there inside, and the variables are all gone. With that, we are supposed to define something called non. Actually, we are supposed to define everything we defined in the previous session, but the thing is, starting that today would be problematic, because anyway we cannot finish the whole thing. So, we rather try to do something else instead of going to non, because we cannot finish non. So, for example, I just get back to the very definition of lambda operation, and I try to show one thing. Well, so if our target is to define L, I add two variables when L is a 2 plus predicate. If my target is to define L and then whatever, I add one variable and all that stuff. We have seen that. Now, what is the advantage? We have seen that splitting is one thing and then defining is one thing. It makes definitions very easy, but then we haven't seen all types of it, right? We will see the types of different lambda expressions. For example, we know that when the thing being defined, as I said, that the thing being defined is the type. So, the type of the thing being defined is the type of the lambda expression. So, it will belong to m e to t. What about lambda x, lambda y, L x y? You can see that it will take one e and then give another e to t, and then finally it will take another e and finally give t. So, this will belong to m e to e to t. So, we can have very complex functions and then define the type of that by using this. We will do a lot of things in the next session. Yeah, I don't want to start this, that is my only problem, but at the same time there is not much left. So yeah, we stop it here. Thank you.